Ohms to neutral impedance, denoted as Z subscript N, is a measure of the electrical resistance and inductive reactance of a conductor or path from a given point in an electrical system to the system's neutral point. It represents the impedance that current encounters when flowing from the point to neutral. The mathematical expression for ohms to neutral impedance is Z subscript N equals the square root of R squared plus X subscript L squared, where R is the resistance in ohms of the conductor or path, and X subscript L is the inductive reactance in ohms of the conductor or path. Ohms to neutral impedance is crucial in voltage drop calculations because it determines the amount of voltage loss that occurs when current flows through a conductor or path. The voltage drop, denoted as V subscript D, is directly proportional to the current, denoted as I, flowing, and the impedance, denoted as Z subscript N. The relationship is expressed as V subscript D equals I times Z subscript N. Several factors affect ohms to neutral impedance. Firstly, conductor resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. Longer, thinner conductors have higher resistance. Secondly, inductive reactance. Inductive reactance is caused by the magnetic field generated by current flowing through an inductor or transformer. It is directly proportional to the inductance of the circuit. Thirdly, frequency. Inductive reactance increases with frequency. Ohms to neutral impedance is used in various electrical calculations and applications, including voltage drop calculations in distribution systems, sizing of conductors and transformers, and analysis of power circuits and fault analysis. Understanding these principles allows for accurate calculations and reliable system design. For conductor resistance, the material is a primary factor. Copper and aluminum are commonly used conductors, with copper generally having lower resistance than aluminum for the same size. The resistivity of the material, which is a measure of its resistance to electrical current, is a key parameter. Different materials have different resistivity values, which directly affect the conductor's resistance. The length of the conductor is directly proportional to its resistance. Doubling the length of the conductor doubles the resistance, assuming all other factors remain constant. This is because the electrons have to travel a longer distance through the material, encountering more obstacles along the way. The cross-sectional area of the conductor is inversely proportional to its resistance. Increasing the cross-sectional area reduces the resistance, as there is more space for the electrons to flow. This is why thicker wires have lower resistance than thinner wires of the same material and length. Temperature also affects the resistance of a conductor. As temperature increases, the resistance of most conductors also increases. This is because the increased thermal energy causes the atoms in the conductor to vibrate more, which impedes the flow of electrons. The temperature coefficient of resistance is a measure of how much the resistance changes per degree Celsius. For inductive reactance, the inductance of the circuit is a primary factor. Inductance is a measure of a circuit's ability to store energy in a magnetic field. A higher inductance results in a higher inductive reactance. Inductance depends on the geometry of the circuit, such as the number of turns in a coil and the area enclosed by the coil. The frequency of the alternating current is another factor. Inductive reactance is directly proportional to frequency. As the frequency increases, the inductive reactance also increases. This is because the magnetic field is changing more rapidly, which induces a larger voltage that opposes the current flow. The presence of a core material in an inductor can also affect the inductive reactance. A ferromagnetic core, such as iron, can increase the inductance of the coil, which in turn increases the inductive reactance. The permeability of the core material is a measure of its ability to support the formation of a magnetic field. The geometry of the inductor, including the shape and spacing of the windings, also affects the inductive reactance. Different inductor designs have different inductance values and therefore different inductive reactance values. For frequency, the standard power frequency in North America is 60 Hz, while in many other parts of the world it is 50 Hz. These different frequencies can affect the inductive reactance of circuits. Higher frequencies are used in some specialized applications, such as radio frequency circuits and high-speed digital circuits. The inductive reactance increases linearly with frequency. Doubling the frequency doubles the inductive reactance, assuming all other factors remain constant. In voltage drop calculations in distribution systems, accurate determination of ohms to neutral impedance is critical to ensure that the voltage at the load is within acceptable limits. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Utilities and electrical engineers use sophisticated software tools to model distribution systems and calculate voltage drops under various loading conditions. These tools take into account the ohms to neutral impedance of all the conductors and equipment in the system. In sizing of conductors and transformers, the ohms to neutral impedance is used to determine the appropriate size of conductors and transformers to ensure that they can handle the expected load current without excessive voltage drop or overheating. The National Electrical Code, or NEC, provides guidelines for sizing conductors and transformers based on the expected load and the allowable voltage drop. The NEC tables and formulas take into account the ohms to neutral impedance of different types of conductors and transformers. In analysis of power circuits, ohms to neutral impedance is used to analyze the performance of power circuits under normal and abnormal operating conditions. This includes calculating the fault current that would flow in the event of a short circuit. Fault current calculations are essential for selecting appropriate protective devices, such as circuit breakers and fuses, to protect equipment and personnel from electrical hazards. Ohms to neutral impedance also plays a role in power quality studies, which assess the impact of harmonic currents and voltages on the performance of electrical systems. Harmonic currents can cause increased losses and overheating in equipment, and can also interfere with the operation of sensitive electronic devices. Fault analysis is another important application. In the event of a fault, such as a short circuit, the ohms to neutral impedance is used to calculate the fault current. This information is critical for selecting the appropriate protective devices to interrupt the fault current and prevent damage to equipment. Protective devices, such as circuit breakers and fuses, are designed to interrupt the fault current within a certain time period. The interrupting rating of the protective device must be greater than the calculated fault current. Ohms to neutral impedance is also used in ground fault protection systems. These systems are designed to detect ground faults, which are unintentional connections between a current-carrying conductor and ground. Ground faults can be dangerous because they can cause electric shock and fire. Ground fault protection systems typically use a ground fault circuit interrupter, or GFCI, to detect ground faults and interrupt the circuit. The GFCI monitors the current flowing in the hot and neutral conductors. If there is a difference in current, it indicates that some current is flowing to ground. The GFCI will then trip the circuit, interrupting the flow of current. Ohms to neutral impedance is also important in understanding the concept of impedance grounding. Impedance grounding is a method of grounding electrical systems that uses an impedance, such as a resistor or reactor, to limit the ground fault current. This can help to reduce the severity of ground faults and prevent damage to equipment. Impedance grounding is often used in industrial and commercial electrical systems. The value of the grounding impedance is chosen to limit the ground fault current to a safe level. This level is typically below the available fault current from the source. Ohms to neutral impedance plays a significant role in understanding and mitigating voltage imbalances in three-phase electrical systems. Voltage imbalance, also known as voltage unbalance, occurs when the voltages in the three phases of a three-phase system are not equal in magnitude or are not 120 degrees apart in phase angle. Voltage imbalance can cause a variety of problems, including increased motor heating, reduced motor efficiency, and premature equipment failure. Ohms to neutral impedance can contribute to voltage imbalance if it is not equal in all three phases. This can occur due to uneven loading of the phases or due to differences in the impedance of the conductors in each phase. To mitigate voltage imbalance, it is important to balance the load as much as possible and to ensure that the conductors in each phase have similar impedance. Voltage imbalance can be measured using a voltage imbalance meter. The voltage imbalance is typically expressed as a percentage. A voltage imbalance of more than 2% is generally considered to be excessive. In addition, understanding ohms to neutral impedance is important for analyzing and mitigating harmonic distortion in electrical systems. Harmonic distortion is the presence of harmonic currents and voltages in an electrical system. Harmonic currents and voltages are multiples of the fundamental frequency, such as 60 Hz. Harmonic distortion can cause a variety of problems, including increased losses, overheating of equipment, and interference with sensitive electronic devices. Ohms to neutral impedance can affect the propagation of harmonic currents and voltages in an electrical system. The impedance of the system at harmonic frequencies can be different from the impedance at the fundamental frequency. This can cause harmonic currents and voltages to be amplified or attenuated at certain locations in the system. To mitigate harmonic distortion, it is important to identify the sources of harmonic currents and voltages and to implement appropriate mitigation techniques. These techniques can include the use of harmonic filters, which are designed to reduce the amplitude of harmonic currents and voltages. In summary, ohms to neutral impedance is a fundamental parameter in electrical engineering that is used in a wide variety of applications, including voltage drop calculations, conductor sizing, transformer sizing, fault analysis, ground fault protection, voltage imbalance mitigation, and harmonic distortion mitigation. A thorough understanding of ohms to neutral impedance is essential for electrical engineers and technicians who design, install, and maintain electrical systems.